Hey everyone, and welcome to the Channel Name Channel. Today, we're diving into the fascinating world of econometrics. Econometrics gives economists the power to use data to test theories and understand economic relationships. It's the bridge between abstract models and real-world reality. So buckle up, because we'll unpack key concepts and terms to navigate econometrics. And don't forget to turn on subtitles for better understanding. You won't regret it. Let's start with the basics. What is econometrics? It's the use of statistical methods to analyze economic data. Econometrics answers real-world questions like, what's the impact of a minimum wage increase on employment? How does education level affect income inequality? Every field has its pioneers, and in econometrics, that title goes to Ragnar Frisch. He, with Jan Tinbergen, laid the foundation for modern econometric analysis. Frisch developed econometric modeling and founded the Econometric Society and its journal Econometrica. Let's talk about a fundamental tool in an econometrician's toolbox: the regression model. A regression model estimates the relationship between two or more variables. The dependent variable is what we're trying to explain or predict, and the independent variables are the factors we think might influence it. Fitting a line through a scatter plot helps determine the strength and direction of their relationship. Multicollinearity might sound like a mouthful, but it's crucial to understanding regression analysis limitations. It occurs when two or more independent variables in your model are highly correlated, making it hard to isolate their effects. It's like figuring out if it's the sugar or butter that makes the cake good when they're always used together. This makes it challenging to determine each variable's true impact. Let's talk about an important concept in econometrics: heteroskedasticity. Heteroskedasticity occurs when the variance of data points around the regression line is not constant. This means the accuracy of predictions varies across different levels of the independent variable. It's like predicting height based on age, where accuracy might be lower for younger ages. Meet the MVP of econometrics ordinary least squares, or OLS. OLS finds the line that best fits our data. It minimizes the squared differences between observed and predicted values. This makes OLS powerful for estimating variable relationships. The Gauss-Markov theorem tells us that, under certain assumptions, the OLS estimator is the best linear unbiased estimator, or BLUE, of the coefficients in our regression model. This means OLS gives us unbiased estimates with the smallest variance, making them the most precise estimates. This is why OLS is widely used in econometrics. In econometrics, we often talk about variables being either endogenous or exogenous. An endogenous variable is one determined by the model, influenced by other variables. For example, education could be endogenous because it's influenced by factors like family background or innate ability, which might also affect their income. Now let's meet the opposite of our endogenous friend, the exogenous variable. In an econometric model, an exogenous variable is not influenced by other variables. For instance, rainfall could be considered exogenous in a model predicting crop yields. We've built our regression model, but how well does it explain our data? Enter the R-squared value, the coefficient of determination. R-squared ranges from 0 to 1, with higher values indicating a better fit. An R-squared of 1 means our model perfectly predicts the variation, while an R-squared of 0 means it doesn't explain any variation. Time series data chronicles an economic variable over time. It's a sequence of data points collected at intervals, tracking changes and patterns. Analyzing time series data reveals trends, seasonality, and cyclical patterns. Enter panel data, a powerful type of data that combines cross-sectional data, data on multiple individuals at a single point in time, with time series data, data on a single individual over multiple points in time. Panel data tracks the same individuals over time, giving us a richer understanding of variable changes. It's like having a time-lapse video of our data, seeing the bigger picture. Autocorrelation happens when error terms in our model are correlated over time. Imagine predicting the weather and consistently overestimating temperature on sunny days and underestimating it on cloudy days. That's autocorrelation. Errors follow a pattern which biases our estimates and makes our model less reliable. In econometrics, we often encounter variables not easily measured in numbers, like gender or occupation, or whether someone lives in an urban or rural area. That's where dummy variables help. They take the value of 1 if a characteristic is present and 0 if absent, allowing us to include categorical variables in our regression models. When dealing with panel data, we often choose between fixed effects and random effects models. Fixed effects models assume unobserved characteristics are constant over time and correlated with independent variables. Random effects models assume these characteristics vary randomly and are not correlated with independent variables. In a perfect world, we could conduct controlled experiments to determine cause and effect in economics, but the real world is often much messier. That's where instrumental variables, or IV estimation, comes in. IV estimation addresses endogeneity, isolating the causal effect of our variable even when tangled with other factors. Sometimes our dependent variable isn't continuous, like income or height, but a binary outcome, like employed or unemployed. That's where probit models come in. They estimate the probability of a binary outcome. Just like probit models, logit models predict binary outcomes. They use a different approach based on the logistic function. Both models often produce similar results, and choosing between them often comes down to personal preference or software used. In econometrics, we test hypotheses to see if our findings are statistically significant or due to random chance. The p-value measures evidence against the null hypothesis, the default assumption of no relationship between variables. A small p-value, typically less than 0.05, suggests our results are unlikely by chance, leading us to reject the null hypothesis. When building econometric models, we often have multiple candidates. One widely used measure is the Akaike Information Criterion, or AIC. The AIC balances goodness of fit with model complexity, penalizing models with more parameters to prevent overfitting. The Durbin-Watson statistic detects autocorrelation in regression models. It ranges from 0 to 4, with 2 indicating no autocorrelation. Testing the Durbin-Watson statistic helps assess independent errors. In econometrics, we work with incredibly diverse data representing individuals, firms, or countries. Recognizing heterogeneity is crucial for accurate models. It's about understanding one size doesn't fit all, and relationships between variables vary across groups. Heteroskedasticity, the problem of unequal variances in error terms, can disrupt our regression models. The Broich-Pagan test checks if the variance of errors is constant across different levels of our independent variables. If heteroskedasticity is present, we may need to adjust our model or use different estimation techniques for reliable results. The Phillips curve is a key concept in macroeconomics, showing the inverse relationship between inflation and unemployment. Though debated and revised over the years, it highlights the trade-offs policymakers face in managing the economy. Remember autocorrelation, where error terms get a little too friendly. It also goes by another name, serial correlation. It's the correlation of a variable with itself over time, often in time series data. Addressing it is crucial for unbiased and efficient estimates in time series models. Endogeneity is the chicken or egg dilemma of econometrics. Determining causality between variables is challenging. Addressing it is crucial for valid causal inferences and understanding true economic relationships. That's it for our whirlwind tour of key econometrics concepts and terms. Hopefully, you now have a better understanding of the tools and techniques econometricians use. Remember, econometrics is ever evolving, and there's always more to learn. Thanks for watching. Don't forget to like, share and subscribe for more insightful content. Turn on notifications so you never miss an update from our Civil Services YouTube channel.